Hi, let's talk about strain tensor today. Before we talk about the strain tensor, I'd like to review the analysis procedure for structural and mechanical system. Regarding any analysis of such a system we need to consider three different conditions. The first one is the force equilibrium condition. Using the force equilibrium condition, we can build a relation between the force, the external force, and then the internal stress tensor. And also we have second condition. Second condition is the compatibility condition. Using the compatibility relation, so we can build a relation between the displacement vector to the strain tensor here. So here there is one-to-one relation like this. And then we can build the flow analysis using the material law. The material law make a relation between the stress tensor and the strain tensor. And then this is a flow of our analysis. If you start from the force and then calculate stress, and the next step we calculate the strain, and then we finish our calculation checking the displacement compatibility. Or we can do another way. We start from the displacement compatibility to measure the strain in terms of unknown displacement variable or parameters. And then using the material law, we calculate the stress corresponding to strain field. And then from the stress, and we check the force equilibrium to finish our analysis. So make sure that here we have, as I told you, I have force equilibrium relation. And then I have displacement compatibility here. So note that these two conditions are independent of each other. So we can build force equilibrium independent of displacement or strain development. And also we can build compatibility relation without thinking the force equilibrium. Okay? So only using the material law we can make a connection between these two conditions. That's how we close the overall solution procedure. Today, let's talk about this, the displacement compatibility to derive the strain tensor here. Okay. Now, before we start our discussion, so let's build a coordinate system. The building a coordinate system is really first step before any discussion in this mechanics. Okay, this is my coordinate. And then let's imagine I have a body here. So before deformation, so I'd like call it the initial configuration of body. And then I have the event of deformation. Say I have an event of deformation, then this body would deform like this. For example, this is a very arbitrary configuration here. So let's consider point P and then also point Q here. Point P and point Q. And then we can construct a vector here to this position. Then this vector is called xp. And then obviously this vector can be named as xq. Okay? And then what is the difference? Between the point P and the point Q, then we have difference here. This is, we can say that delta x. This is the difference vector. And then this is what? This is, that represent a segment, isn't it right? The segment between a point P and Q. And this segment can be represented by this vector delta x, capital X here. So now let's consider after deformation. After deformation, the point P is displaced to the lowercase p here, and the point Q is also displaced like this, Q, lowercase q. And as before, we can build a segment here, segment vector, and then this is after deformation. I'd like to denote this delta lowercase x. This is vector 2. Okay? And then using the vector mechanics, so I can write the segment, the initial segment delta x can be represented by its size and then its direction and x. And also after deformation, this segment also represented by the size, lowercase size, or I mean the after deformation size, and then its direction after deformation. Okay? Alright, so here I considered 2 points a little bit away from each other. But in continuum mechanics, we want to consider these 2 points are very close to each other. And then understandably, we can change it to dx instead of delta. And also, this is also written as ds. And then the direction is same. Also here too. Okay? So now, from now on, let's use this notation. So I'd like to use this notation here. These two notations. Okay, so at first, I'd like to compare the size, okay, the length of the segment before and after deformation. The length of the segment after deformation is lowercase s, is given as in terms of the initial length, the capital S, but we have length change, isn't it, right? So which means you can represent it by 1 plus or certain kind of the fraction of length change. Here the epsilon is the fraction of length change with respect to the initial length of the segment. And then make sure that here we have two different vectors here. The before deformation and then also the after deformation here. Okay? Then because this is given as a vector, and then its length can be measured as square norm of a vector. But handling the square root is not that convenient. Instead of handling the square root, I'd like to compare the change of square norms. So then I can write dx dot product dx minus the square of initial length and divide by square of initial length. Okay, so using these two relations, I can simplify this relation. That becomes the size, small size square, and then it's normal dot nx, the minus the initial segment square, the length square, and then the dot product is normal. So make sure that this is unit normal. That's why this is equal to 1, isn't it? This is equal to 1. Okay, so we can drop it. Now also in denominator, so I have same expression. So that is simplified using this relation, and this is simplified as 1 plus the epsilon, the fraction of the length change, square the capital S square minus t capital S square divided by t capital S square. So here cancel, and then this is equal to epsilon plus the epsilon square. That's what we can obtain. And then we can write dx here. Dx is what? Dx is equal to the initial segment plus any displacement change du, isn't it, right? So let's plug that expression here, and then let's rearrange this equation using this. Then what happens is we have what? We have the initial segment and then du dot initial segment plus displacement segment, and then minus dx dot dx dot, the initial one, divided by the initial dot. And then this is equal to what? This is equal to, if you expand this, so we have 2 of du dot dx plus du dot du, and then divided by dx dot and dx. Okay, then let's plug this expression here. For example, here, this guy. So dx is equal to the length times its direction. So let's plug that relation into here, and then divide the length, the numerator and denominator at the same time. So what you can obtain is 2 of du dx, sorry, du not ds, is length, and then dot normal plus du with respect to ds, the initial length, du vector, and then ds. Okay, so let's compare these two equations together. So if you compare these two equations together, we can conclude that here the fraction of length change is equal to this, the first term of this equation, and the epsilon square is equal to this. Okay, so now let's talk about this term furthermore. Okay, and then the fraction of length change, the epsilon, the fraction of length change, the epsilon is equal to the derivative of displacement with respect to initial length, and the dot product, the direction of the initial segment. The physical meaning of this term is, this is what does it mean? This is equal to, this is the displacement vector. Displacement vector per unit initial segment. That's the physical meaning of this. In other words, we can call it, this is strain tensor, a strain vector, sorry, strain vector. It has only one index, which means the fraction of the strain can be obtained like this. The fraction of strain can be obtained by means of the strain vector and then normal vector, dot product between this. The physical meaning of this, the fraction of strain, the fraction of length change is the projection of strain vector into the initial direction here. Okay? Okay, so now let's talk about this strain vector furthermore in detail. So the strain vector is equal to du and then ds here. So now let's use chain rule. If you use chain rule, so we can rewrite that relation by means of the initial coordinate, and then sorry, this is full derivative dxj with respect to the initial length. Okay, and obviously this term it becomes the unit vector. So this is equal to du I dxj and j, the same as before. So here I'd like to look at this term in detail. So this is not symmetric, the matrix. Okay, the I is from 1 to 3, and then the j is from 1 to 3. Okay, so this is a 3 by 3 matrix, but this is not symmetric. So any arbitrary the matrix can be represented by sum of symmetric part and then anti-symmetric part. So here we can write ui and then xj can be written as a half of ui and xj plus, and then uj and then xi plus, and a half of ui and xj minus uj and xi. So first part is the symmetric part. This is the symmetric part. And then this is anti-symmetric part. So if you compare this equation together, here this part and this part cancel each other. So it recovered the original formation. And then this symmetric part, we write the symmetric part Eij, and then this anti-symmetric part, typically we use omega ij here. And then the strain vector can be represented by the symmetric part of the tensor plus, and then anti-symmetric part, and then this is a dot product into its direction, nxj direction. Okay, that's how we can obtain this. So make sure that this guy is equal to, in the case of a small rotation, that represented a rotation. In the case of small deformation, then we can drop this. In the case of small deformation, rigid body rotation is not that much. That's why the strain vector can be approximated as epsilon I is equal to Eij and nxj. That's how we write this. And then we call this is strain, small strain tensor. Okay, that's how we obtain the expression of small strain tensor. This small strain tensor is widely used in various applications. This is small strain tensor here. So if you take the finite element classes, in the case of B matrix, the structure of B matrix is given in this way. Okay, so let me stop the talk about the small strain tensor today.